investigator on the DARPA-funded SafeDocs research program. I'm also one of the 2 project leaders of ISO 32000, which is the core PDF standard. Today I'm here to provide an update to industry on the SafeDocs research program. My focus today is on how you can apply our intermediate outcomes to create better, more reliable and trustworthy PDF processes. The ultimate vision of SafeDocs is a seismic shift away from addressing vulnerabilities of parsers from being an entirely reactive process with constant patching and hotfixing in response to threats, to a proactive approach where provably correct parsers get created that are inherently impervious to vulnerabilities by their very design, with all the necessarily formally backed proofs that entails. So the goal of the SafeDocs program is to dramatically improve software's ability to detect and reject invalid or maliciously crafted input data without impacting the key functionality of new and existing electronic data formats. SafeDocs seeks to create technological assurance that an electronic document or message is automatically checked and safe to open, while also generating safer document formats that are subsets of current untrustworthy versions. The SafeDocs project is now just 2 years into its research and has already achieved a number of significant outcomes. Although this end goal is not yet fully realised, there are significant outcomes that can assist industry and everyone who uses PDF. Today I'll present some of what's been achieved and how you can take these intermediate results and apply them to your business today. The 2021 CWE Top 25 Most Dangerous Software Weaknesses is a list of the most common and impactful issues experienced over the previous 2 calendar years, as recorded in the US MITRE organization's vulnerability database. As MITRE states, these weaknesses are dangerous because they are often easy to find, exploit, and can allow adversaries to completely take over a system, steal data, or prevent an application from working. Although many are expressed in a web-centric manner, a number of these top 25 are highly relevant to PDF, or parsing of any format. Number 4, improper input validation, is clearly related. In our context, it means checking that an alleged PDF file is really a valid PDF before we attempt more detailed processing of its data. Potentially as a consequence of incorrectly or insufficiently invalidated input, number 1 and number 3, for reading or writing out of bounds, can also be caused by parser shortcomings. The score for each weakness reflects the combination of prevalence and severity. When we sum the scores for these 3 weaknesses alone, it is 1/3 of the total score of all weaknesses, indicating the importance that reliable input validation or parsing holds for correctness and surety. So if we can get input parsing right, we should be well on our way to a better, more secure future. And how do we get input parsing better? Let's start at the beginning with the specification of the file format for what we are trying to parse. PDF, like most non-trivial file formats, is defined by a prose-based file format specification document. This attempts to define how a compliant file is defined and what it is and is not allowed. It is not an implementation guide nor a software design, but it is essential reading for anyone attempting to write a parser. In any free text prose-based specification, there will always be ambiguities, mistakes, contradictions, errors of omission, as natural language is just not as precise as programming languages, so any official format specification is certainly not a perfect document. If we overlay every file in existence against any nominal spec, what I call the universe of all extant data, then we have 2 areas of interest, and this is not shown to scale. There is the unimplemented portion of specs where no extant data exists. This can be because it is either a very new feature and no applications generate such data, or it can be because the feature never met market needs or was so poorly specified as to be effectively unimplementable. In a perfect world, obsolete features get removed from a spec as they only add to confusion and complexity. And then there is the malformation and extensions area, for which the core official format specification has no definition, but creators have intentionally or unintentionally created data and thus a de facto specification. By de facto specification, I mean the real-world format spec that does not exist in document form, but is what has been implemented by a majority for interoperability reasons. In the case of PDF, this probably includes various errors with cross-reference tables, possibly certain misspelt key names, and general permissiveness as white space, etc. If an arbitrary corpus is then created, either for research or for test purposes, then such a corpus will be some distinct subset of the entire universe. By definition, it cannot contain files with features from the unimplemented region, but it will also unwittingly include files with these malformations and extensions. In the case of PDF, we know that various classes of documents are also underrepresented in Internet source corpora, and that not every aspect of every PDF feature will get covered by any corpus. This is because such classes of document may contain confidential, personal information or intellectual property, and thus specific file format features supporting these document classes may not appear in a randomly sampled corpus. At the same time, it can be appreciated that not every parser for a file format will be able to parse every file in existence, or even every file in a large corpus. And every parser will also likely implement a different subset of a complex file format, again either intentionally as a business decision or pragmatic engineering choice, or unintentionally, such as referring to an outdated spec, integration with some software modules that are not fully featured, or implementation bugs. This is what SafeDocs refers to as a parser differential, but what you might see as differences between implementations. Implementation bugs can also be so severe that a parser may accept and process files that are clearly outside any understanding of the specification. Formally, this is known as a weird machine and is an area that attackers love to target. As real-world infamous examples related to PDF, here are some less than minimal, off-the-chart, non-compliant PDFs that certain parsers accepted back in 2017. I won't explain these except to say that about the only thing that might make these PDFs is the file extension or what an HTML header or MIME type said. So each of these areas in this diagram represents some form of truth that gets referenced in any corpus-based research development. The only stable, common ground truth baseline is the official format specification. If this can be improved, then everything gets lifted up, or at least a little. So this will be the focus for the rest of my presentation. These ideas and issues are certainly not unique to PDF. HTML has many idiosyncrasies that have been written about, and even something supposedly as simple as JSON is a minefield. In the process of putting the PDF specification under a spotlight and attempting to methodically encode all of its syntactic, data and integrity requirements into data definition languages and into the Arlington PDF model, a number of issues with the PDF spec have been identified. This includes the use of imprecise language, inconsistencies, missing and incorrect information, and a few more serious errors. Many issues have already been fixed in the December 2020 edition of PDF2, published as ISO 32000 Part 2 2020. More recent issues are logged in the PDF Association's public GitHub repo and then discussed in the PDF Technical Working Group with an industry recommendation openly published by the association. These resolutions will also be passed to ISO for incorporating in any future publications. The highly methodical process of trying to encapsulate the full PDF specification into formal data definition languages, or DDLs, highlight any shortcomings in the spec, because it is a much more rigorous process than the mental interpretation done by developers into their programming languages of choice. Data definition languages work hand in hand with theorem provers to reason about the format, which also highlights inconsistencies and ambiguities that may not be obvious to developers. From a SafeDocs perspective, a clear, precise, complete, and unambiguous file format specification will lead to less error-prone parsers. An unambiguous specification also directly lends itself to machine readability. It enables formal reasoning and allows automatic code and data generation. DDLs have also been used to create prototype secure parsers, which have been run against hundreds of thousands, likely millions of extant PDFs, and common differences have been discovered. This reflects what SafeDocs refers to as the de facto specification, that is the specification that parsers actually implement, and it is different to the official rulebook of the ISO PDF spec. So not only has SafeDocs found issues with the official spec, we've also been able to assess the de facto specification and better align practice to spec. Although you may feel that some of these issues are trivial, my next few slides will hopefully demonstrate the need to get more scientific about the way we define and work with file formats. So let's start simple, just knowing which fonts exist in a PDF. Reliable text extraction from PDF documents is important for many businesses and users, whether it be indexing, search, or other processing. And when you think about PDF text extraction, you must also consider all the font objects in PDF. Yet how do you assess whether a text extraction tool considers everywhere in the PDF file format where text and fonts may exist? Using a methodical approach in analysing the PDF objects, we know exactly where all font objects can reside within a PDF document. We've also realised that there was a big discrepancy in what tools reported. And please note, this is not about the ins and outs of specific font formats or data integrity rules between keys across a multitude of font dictionaries, but it is just about knowing if a font is present at all. Pretty fundamental stuff that has not changed for many, many years. Unfortunately, many tools, including both command line and visual, have not taken a methodical approach and fail to correctly identify all places where fonts can exist in a PDF. Does this also mean that these tools will not fully identify text or perform other text-oriented operations correctly? You begin to wonder. This is really not rocket science, but methodical engineering, but it does demonstrate some of the challenges we face in the PDF industry and the need to get more methodical about things. You might feel that we should blame the PDF spec itself, as this logic might be hidden in varying terminology used in the 1,000-page document. Such issues undoubtedly impact end users of PDF. You can find various test cases of a similar ilk in the PDF Association SafeDocs GitHub repo under the Miscellaneous Targeted Test PDF folder. But let's move on to something more complex. PDF inline images can use abbreviated key names for convenience and compactness, or they can use the full key names from ImageX objects. They are also unrestricted in mixing key names from both these sets. Although the PDF specification explicitly prohibits identical or duplicate key names, it's silent on how to handle this special situation where two different key names have an identical semantic meaning. And inline images have been in PDF since PDF 1.0, so it has taken over 25 years to find this issue. This issue was raised with the PDF Association's PDF Technical Working Group, and the industry agreed resolution to this issue is to add an additional statement. In the situation where both an abbreviated key name and the corresponding full key name from Table 91 are present, the abbreviated key name shall take precedence. I have created and published a handcrafted PDF test file in the PDF Association SafeDocs GitHub repo under the Inline Image Abbreviations folder. This test PDF contains 8 separate inline images with different full key and abbreviated name collisions. In each case, correct processing of the abbreviated key name in preference to the full key name should result in the letters IMG on the yellow background. The green rectangle is just an RE operator placed beneath each inline image just prior to the inline image paint operation. A perfect implementation is thus 8 yellow IMG images. Obviously, this industry resolution is very new, so we cannot expect every viewer to correctly render this PDF file yet. The screenshots shown here are all from different PDF viewers, and as you can see, there is a huge variability. This discovery and resolution also illustrates a few key points. Firstly, close scrutiny of a prose-based specification can find issues no matter how well read or old it is. And 2, how widely different a PDF can render for such a corner case. With knowledge of what PDF viewers are used within an organization, a targeted phishing attack could utilize this to display different information to users depending on their viewer. From early SafeDocs evaluation of parsers, it was clear that a number of PDF parsers did not correctly follow all of PDF's lexical rules. Some only worked with excessive whitespace or line breaks, while others did not support null, the 0 byte, as a valid PDF whitespace character, probably because they used the whitespace rules or whatever programming language they were written in. And if a PDF processor cannot get PDF's lexicals rules correct, then everything downstream from there will be less than ideal. Fundamentally, there have been no changes to the lexical rules of PDF as defined in ISO 32000. However, wording has changed over the years. Most recently, corrections, such as recognizing that left curly brace and right curly brace are not token delimiters in general PDF, but a hangover from PostScript, and clarifications, such as improved cross-referencing to other clauses and highlighting the double character constructs used by dictionaries, have all been made, but the rules are unchanged. On the right at the top, you can see some PDF fragments, which everyone will hopefully recognize as valid but compact, meaning they don't have a lot of white space. It is common to see adjacent PDF name objects without white space, and nested arrays and nested dictionaries. The reason these are valid is because PDF very clearly defines a set of token delimiter bytes. When we methodically apply the set of allowed token delimiter bytes, we can create a token adjacency matrix of all 121 possible combinations for pairs of tokens. Note that this does not necessarily mean that all such token pairings are needed by ISO 32000, but a robust PDF lexical analyzer needs to reliably handle any input. That is the point of a parser after all. On the right at the bottom, you can see the 4 test cases for an array's closed token, the right square bracket, compactly followed by a PDF real number. A PDF number can obviously start with a digit, but it can also start with a plus, a minus, or a decimal point, thus creating 4 test cases which all need to be handled correctly. These 4 test cases represent what is required for the single cell in the test matrix shown here. So you should appreciate the resulting total number of test cases required to get full and thorough coverage. I've created a compact test file for testing PDF lexical analyzers to ensure that they comply with the finer points of lexical analysis and token delimiters, and to ensure interoperability between implementations. Tests exist for PDF body, where normal PDF objects are defined between obj and end obj keywords, as well as within PDF content streams. In the PDF Association's SafeDocs GitHub repo, you will find the handcrafted PDF file along with the documentation matrix shown here. Note that the PDF test file cannot be tested via visual output. A developer must look at the token output from a lexical analyzer and be watching for errors or skipped bytes, as there should be none. In most processes, such issues will be unreported and silently ignored. This test PDF has been successfully used to find and report issues against several open source PDF parsers, so I encourage you to share this with your development team. In the terminology of the theories that underlie SafeDocs, dialects are small variations in a grammar, and they can often be pitfalls for programmers who fail to recognize and explicitly code for them, or who code them incorrectly. In PDF, there are a few such dialects that we can encounter. Firstly, the occurrence of an inline PDF dictionary within a content stream. An initial gut reaction might be that that is not allowed, since all resources are referenced via names. However, on closer examination, there are a few places where PDF dictionaries can validly occur inline in a content stream. Firstly, in marked content property lists, and with the explosion of tag PDF, this has certainly seen less capable PDF parsers scramble to implement this support. Secondly, in custom inline image dictionary keys, since this is otherwise a regular dictionary, excepting for the start and end tokens now being operators. And finally, in a compatibility section denoted by the BX and EX operators. Within a compatibility section, PDF states, unrecognized operators, along with their operands, shall be ignored without error until the balancing EX operator is encountered. If we then think about what a lazy programmer might do, or someone who doesn't bother reading the spec, it is conceivable they will just hook in the code used in parsing objects in the PDF body, since that seems like it should just work, unquote. However, a subtle but important difference is that indirect references are never permitted in content streams, with clause 7.8.2 content streams explicitly stating indirect objects and object references shall not be permitted at all. I have developed positive and negative test cases for this specific dialect of PDF, which you can find under the dialect folder in the SafeDocs GitHub repo. These test files are viewable in a text editor, although they are binary files like all PDFs, so do not edit them. Note that unlike in the compacted syntax PDFs, these test files have whitespace to aid readability. Last week I devoted a whole PDF Day session to explaining and demonstrating the Arlington PDF model, so I won't go into much detail here. Suffice to say, the Arlington PDF model is the first open access, vendor and implementation neutral, specification derived, machine and human readable comprehensive definition of all PDF objects in the PDF document object model. It does not replace the PDF spec, but sits beside it and reflects a stable ground truth that both machines and humans can share unambiguously. It is a set of lightweight, text-based, tab-separated value files with 12 columns of structured data and a set of custom predicates that directly express wording from the spec. This allows the Arlington model to express integrity and data relationships between the 515 objects that comprise the PDF document object model. It is platform and programming language agnostic and can be used directly as is with a no-code approach, as I demonstrated last week, can use a low-code approach with scripting languages such as Python and the Jupyter Notebook I also demonstrated, or you can build on our larger proof-of-concept implementations in Java, Python, or C++. We also validated the Arlington model against a proprietary model, as well as a large corpus of extant data, and you've already heard about some of the outcomes from these discoveries earlier during this presentation. In this process, we discovered many issues in PDF, with several being fixed in the December 2020 edition of ISO 32000. If you'd like more information on the Arlington PDF model, please refer to GitHub repo, where other publications and presentations are provided. Last week, Tim Allison presented his PDF Day session on making sense of PDF structures in the wild at scale. This presented what we refer to as a PDF Observatory, which provides a magnifier to millions of PDFs at a time. I do not intend to cover what Tim already explained, but instead I will highlight how such a big data system can provide us, the PDF industry, with additional insights. The concept of an observatory is based on the Electronic Frontier Foundation's SSL Observatory, which is a project to investigate the certificates used to secure all of the sites encrypted with HTTPS on the web in order to search for vulnerabilities, document the practices of certificate authorities, and aid researchers interested in the web's encryption infrastructure. So our PDF Observatory has fundamentally the same role, just with PDFs, which are arguably larger and more complex than certificates. Our observatory also has a multitude of PDF parsing tools beneath the hood, and we can monitor how each of these parsers performs against different data universes. Tim explained how he had to refetch large portions of web crawls to overcome file truncation limits. This means that the data in our observatory is truly representative of what is on the web. We saw in Tim's presentation how big data trends can become more visible. Tim showed us a heat map of where PDFs are hosted around the globe with some interesting commentary. We could overlay this with PDF versions or specific PDF features such as encryption or digital signatures or annotations. And Tim also showed us detailed results of text extraction from these PDFs and how comparisons between these tools could highlight potential issues in specific tools. In his case, Italian in Apache Tika. This is the power that big data can bring. Because our observatory disassembles a PDF into its constituent key value pairs and its metadata, we're able to look at occurrence rates of specific PDF features or syntactic forms. And we can identify trends in errors in PDFs with knowledge of how often they occur, where and when they occur, and likely the technology that was at fault. I don't want to say we can name and shame, but Tim gave us an example where we're able to assign a particular malformation to a particular PDF producer. The observatory is still very much a work in progress, as Tim explained. The vision is to provide a PDF observatory in a box solution for organizations so that you can apply this technology to your own private corpora, whether that be cloud-based or on-premise. We also need to improve the usability, documentation, and integrations with tools, as Tim also explained, so this is not something in the very near future. However, the PDF Association hopes to use the PDF Observatory, its unique capabilities, and its vast numbers of PDFs to build a report on the global state of PDF. This won't be a super technical deep dive, but a state of play of PDF globally. I will be reaching out soon to learn what you might like to know about PDF, so please think about what would be valuable to you and your organisation. Now that you've had a brief understanding about how SafeDocs has tried to study PDF at a tremendous internet scale, we'll also appreciate that there is a desire and a need to more rapidly identify and locate outliers. A huge corpus that is largely homogeneous will consume lots of CPU resources and not identify things of interest rapidly, so a low turn on your investment of time and money. With an earlier phase of SafeDocs, I had a realization that attachments on bug reports and the issue trackers for other PDF processors would be a rich source of potential outliers, so living the mantra of learning from other people's mistakes. However, issue trackers and their attachments are not indexed by web crawlers and made available via search engines, so these files remain elusive. With support from both JPL and the Apache Tika and PDF Box teams, SafeDocs crawled, collated and packaged over 31 gigabytes of 32,500 alleged PDF files from 32 diverse PDF technologies where their issue tracking software is publicly accessible. By ensuring a variety of programming language and PDF application, this corpus has already proven itself to have a far higher ROI in uncovering latent defects in other PDF technologies. As the tweet says, some of these are the devil's work. The Apache Tika team has also expanded this approach of crawling and mining bug databases for other critical file formats with continued great success. So this is not an approach that is unique to PDF. If you happen to process XMP, then Apache Tika has a growing collection that may interest you. I encourage you all to utilize this free, reasonably sized corpus as a means to stress test your PDF technologies with good ROI. Each file is labeled after the bug identifier, so if an issue does occur with your technology, your engineers can easily track back to the original bug report in the open source project and read the analysis and description there. Again, accelerating your quality efforts and increasing your ROI. All these PDFs are publicly accessible, however, we have not scrubbed them, and you should practice good cyber hygiene when using this corpus. In the future, we hope to continue to expand the breadth and scope of the issue tracker corpus, as well as refreshing to obtain the latest triggering PDFs for the most recent defects. In addition, the PDF Association's PDF Corpora GitHub repository provides information on other PDF-centric corpora, and we will gladly accept contributions of other relevant corpora. SafeDocs is not alone in this fight for establishing formally verifiable parsers. Similar efforts to SafeDocs, but on a smaller scale and with a slightly different focus, have been occurring within Microsoft and as part of Project Everest. Project Everest and the Microsoft EverParse tool have been looking at provably secure communications by modelling part of the C programming language, including its memory model, stack and heap allocated arrays, machine integers, C string literals, and a few system-level functions from the C standard library, enabling formal proofs. They have formally verified important security protocols such as TLS, as well as implementing formally verified high-performance cryptographic libraries used by Mozilla Firefox, Azure, and the Signal app. They have also applied formal methods to boot protocols and firmware, ensuring that each layer of firmware and software in a device's chain of trust is measured and those measurements are reliably recorded for subsequent verification. So this approach is valuable and it can and does work in real life. In the future, we hope that SafeDocs and EverParse can collaborate, and I personally hope that this collaboration can include PDF and PDF-related file formats. This idea of a chain of trust with firmware and boot protocols is not unique. You have no doubt heard similar terms related to digital certificates. But do you ever stop and think that every PDF file also has a chain of trust? Although robustly processed, many parsers blindly trust cross-reference tables, cross-reference streams, trailer dictionaries, incremental updates, and the overall PDF file structure in constructing a virtual index to each object. As you would appreciate, this is the data that effectively defines the location of each object that a parser will then reference. So if this data is not checked, it may all be too late. Recent research has already demonstrated successful attacks against several PDF parsers by manipulating this kind of structural data. SafeDocs has started work on formally modelling and methodically defining this PDF chain of trust. ISO TC 171 SC2 Working Group 8, the working group responsible for PDF, has also started up a discussion group on securing PDF, which is looking at the same topic but from a less formal direction. So this is a new area I believe will be important for PDF parsers, and I'm looking forward to seeing outcomes in the near future. SafeDocs also still has work to do on improving and expanding the Arlington PDF Model, the PDF Observatory, and creating more targeted test cases for issues, as well as improvements to the data definition languages, models, and development environments used to encode PDF and the other file formats, streaming data formats, and protocols being studied. Prototype toolchains are already able to generate formally secure parsers while making reasoned statements about the captured requirements, including highlighting the issues underlying what I've presented earlier. All these efforts will no doubt further find issues in the specifications for whatever formats are analysed. These issues then need to be resolved by experts and communicated to industry so that implementations can be checked and hardened as necessary. SafeDocs is also starting work with the ICC and ISO on ICC Max, which is the next ICC color profile format, to review its flexible calculator element for any inherent design weaknesses that might be used as attack vectors in core operating systems or embedded in other file formats like PDF. The preliminary work alone has already highlighted a number of issues in the ICC2 spec regarding the ICC file layout that will hopefully soon be fixed. This talk has hopefully helped you understand some of the industry-relevant outcomes from the DARPA-funded SafeDocs research program. This work has been aimed squarely at reducing the attack surface of parsing software and identifying and removing weaknesses in the file formats, including PDF and its nested formats, with a focus in removing ambiguities from the specification. Outcomes you can use today include the various PDF test files in the PDF Association's SafeDocs GitHub repo, the issue tracker stressful corpus comprising thousands of stressful PDF files, the open source, vendor neutral, specification derived, machine readable Arlington PDF model definition of all PDF DOM objects. In the future, we hope to open up the PDF Observatory and share our work on formalizing the PDF chain of trust that leads to a canonical understanding of the PDF file structure and all objects in a PDF. I hope that you have seen how SafeDocs has been able to bring a new bright light to PDF and has worked with the PDF Association so that these intermediate outcomes can have an immediate impact on your bottom line. Thank you for your attention. I'll now hand back to Duff for questions.
All right, thanks very much, Peter. Let's get you up there. If you want to put up a slide, you can do so. And do have a couple questions for you here.
I won't put up a slide. Maybe depending on the question, I can put up a
Sure.
slide from the deck if necessary.
Okay, first question here. I should mention, first of all, that the slides from your presentation are available in the handouts panel here. So first question, you mentioned that SafeDocs can already automatically generate parsers. Are these PDF parsers? How good are these parsers?
Yes, so yes, they are PDF parsers. So the way that it works is that the grammar for PDF is defined in what we call a DDL, a data definition language, and then that can be cross-compiled into various programming languages, C, C++, Haskell, and some other sort of more esoteric ones. And then these can parse PDFs. Now, when I say parse, it's literally just parsing. We're not making a renderer or not making a text extractor. But yes, they're fully blown parsers. They perform fairly well. We're baselining against some open source implementations written in C and C++. These parsers are of equal speed and equal memory. In some cases, they're faster. In some cases, they're slower, which you would expect across a large corpus of files. And then one of the sort of the tests that we do in SafeDocs, for example, is we make the researchers have to implement a new feature in PDF and see how fast they can turn it around. And now that one of the metrics we have for success is measuring the lines of code of a DDL, because obviously something is smaller, it's much easier to look at and much easier to cope with. So the DDLs are typically around half to like 12% of C++ parser source code. So yes, they do PDFs. Some of them are available. I had the acronyms in my slide deck, and I can certainly point you at the GitHub repos for where this research work is occurring.
Okay, great. So you showed a number of very, very specific PDF tests. Does this imply that you're making test files for every issue that is being identified?
Oh, no, not at all. We make files specifically when there's maybe a bit of confusion about what's happening. So the way this is detected is that our parsers, which are automatically generated, are very strictly adhere to the PDF spec. And there is no sort of permissiveness or having to think about whether something should be, whether I should code it up to allow this PDF file through. It's basically very strict interpretation of the PDF spec. We run it through, for example, the Observatory files or files of that quantity, detect issues, and then depending on what's discovered, it may need a bit of further research so I can explain to the researchers exactly what they found. And in the case, I think the classic case is the inline image issue. So this was actually picked up when they started to code this. One of the performers, actually their theorem proof, their program behind the scenes that says that this parser is valid and formally proved, actually failed. And it was failing because it was saying there were two ways to express various things in an inline image. And it was sort of saying this makes no sense. I can't resolve how you can determine, what the size of an image is or what the length of an image is or whatever it was. And so we created a test file to sort of see how other black box technologies operated, and that was the reason they were created. I certainly don't intend to create a test case for every single change that we're making to the PDF spec. That's just too much.
Sure. So it seems that many of the issues with PDF that you showed are not specific to PDF security per se. How do they relate to SafeDocs' goal of stopping malicious input?
Okay, well, I guess we just need to think about SafeDocs' goal. It's actually much more than just malicious input. It's about having reliability and trust in what we see in our file formats, whether it be a PDF file and you're viewing it on your screen, or a Word document, or even an image file. SafeDocs' goal is to make sure that these things are actually repeatable. In my deck, I gave some references to JSON parsing. I think many people would appreciate that JSON is a very simple file format, and really, how hard can it be? And it's really surprising when you read these articles on sort of how hard JSON is, and you realize that in actual fact that it's much, much harder than you think. So I think it's not about security in the PDF sense. It's much more about having a format with its clear and concise and unambiguous definition that everyone can understand, and there's not a lot of mental interpretation done by programmers, which can obviously vary depending on who you are and maybe your background and how much you understand PDF. So the goal of SafeDocs is not really about security in the PDF sense. It's much more around reliable output and reliable parsers that all do the same thing, albeit still wanting to have product differentiation and unique capabilities in those products.
So one additional question here is what is for me actually. What do you mean by formal reasoning?
Okay, so formal reasoning means the ability to look at a parser or to look at some input and say, yes, that will converge. So for example, there are no possibilities of inputs that will create an infinite loop. And we see this in PDF, obviously, where parsers can get caught up with cycles. We use indirect references in PDF to make a loop in our PDF file where one object refers to another, which refers to another. And that loop can, in a malicious PDF, refer back to the first object, and there we have an infinite loop. So the formal methods are able to detect that logic in the input, even if we as humans can't see it obviously in the spec. It's also about knowing that something is uniquely defined, and the example of the inline image is where two bits of information, being the abbreviated key and the long key, both were trying to define the same semantic object. And there was no rule that was implemented which said which one had precedence or something like that. So the formal reasoning is that logic that goes through and analyzes all this. And this is for every key, every value, every object, all the lexical rules, and in the near future, hopefully all the structural rules in PDF, because obviously you're building on previous things that happens in the parsing pipeline. So hopefully that makes sense.
Yep. So last question I have here is it's asked, is there also a way to test PDF file creation, and if this is valid syntax?
So that's a really good question, actually, because obviously, a parser's input is the output from somebody else. At the moment, so the DDLs that are created in SafeDocs do generate parsers, but they can theoretically be used to generate what in SafeDocs terminology is called an unparser. We would call it a PDF writer. It's a little bit of a harder problem because there are slightly different rules and so forth when we're creating PDFs. At the moment, the best thing would be to use the Arlington model. It's a hard baseline against the spec. It's not attempting to be an implementation and permissiveness or anything like that, or trying to render something. It's solely looking at the data objects and making an assessment as to whether that is valid or invalid according to the latest spec. So I think the answer to the question, I would think, is use the Arlington model and its proof of concept applications that were written in C++, the test grammar application.